Hello everyone, welcome to this introduction lecture to geodynamics. First thing I want to do in this lecture is to introduce some of the resources I have used to prepare the lecture. There is an essential book on geodynamics, which is simply called Geodynamics, and which was written by Donald Turcotte and Gerhard Schubert. This is a very useful book to study the physics of geodynamic processes. Another essential resource that has been used to prepare this lecture is Google Earth. You will see a lot of Google Earth pictures later in the lecture. So let's start with the structure of the Earth. As you all know, the Earth is spheric and has a radius of about 6,400 kilometers. This distance is approximately the distance between the Brittany, the western part of France, to Kyrgyzstan at the other side of the Eurasian plate. So that's just to give you an idea of the order of magnitude. Let's start from the inside. We have the inner core. So the inner core has a thickness of about 1,300 kilometers. It is supposedly solid, while the outer core is liquid, and it has a thickness of 2,200 kilometers. The lower mantle, which is the outer shell here, in this picture, has a thickness of 2,100 kilometers approximately, and the next shell would be the upper mantle, which has a thickness of 660 kilometers roughly. The most outer shell looks very tiny on the picture, which is to scale, and this is the crust, and the thickness of the crust will vary between 0 and 70 kilometers in the regions of intense thickening. Now I want to define an important layer which has not been listed yet, and this is the lithosphere. So the lithosphere will be essential because it is the association of the crust and what we would call the rigid part of the upper mantle. So the lithosphere is not the upper mantle plus the crust, it's only a part of the upper mantle, the rigid part. The oceanic lithosphere has a thickness that ranges between 50 and 150 kilometers. The continental lithosphere is notably thicker. It has thickness on the order of 200 to 300 kilometers, so it's thicker. And the question I would like to ask you now is, how do we actually know all this information about the structure of the Earth? This is thanks to the knowledge that comes from seismology. So as you know, seismic waves of triggered by an earthquake somewhere in the Earth travel through the Earth, and they go through all of these layers. Since some of the layers are solid and other liquids, there are some conversion of waves, and waves are being reflected and refracted across the different interfaces, and by studying all these interactions, the seismologists could come up with an internal model of the Earth. The next question that I want to ask you is, how do we know that the Earth's surface has evolved over geological times? And this is thanks to the combination of knowledge from many disciplines, including geology, tectonics, paleogeography, and, for example, geophysical studies such as GPS. So here you see a map view of the Earth, so that's a 2D projection. You see different major plates. Here, for example, the Pacific plate, which is highlighted here in the middle. And you have arrows, and this comes from a GPS model. These arrows, they indicate the relative motion of the plates. So it's the motion of a plate with regard to another. The largest arrows you will find on this plate are located on the Pacific plate. It has a relative motion of about 10 centimeters per year. That's the maximum velocity which is nowadays measured on the surface of the Earth. You can also see that the plate is well defined because all the velocity vectors are oriented in the same direction. So the plate is moving as a more or less rigid block. So another very nice movie I want to show you here is the breakup of Pangea. So this is the result of a plate tectonic reconstruction that actually combines all the data that is nowadays available. So the movie starts at 200 million years. So you see Pangea is here and it's going to run forward in time until the present, and you will see some very important process happening. So you have the opening of here the motion of India that will come closer to Eurasia, the opening of the Atlantic on that side, and then it continues. You see the opening of the South Atlantic comes later, and now India is moving towards Eurasia, and it's going to collide with Eurasia to form the biggest mountain belt on Earth in the current days. So yes, the Earth is dynamic, plates are moving, and that should be linked to internal motions and dynamics of the Earth. As a result of all this motion, we have about 14 major plates at the surface of the Earth. They can be oceanic and continental plates. Some plates have both oceanic and continental portions. The deformation, since plates are moving as coherent blocks, the deformation has to be mostly located at plate boundaries, but it's not only the case. There may be deformation inside plates also. The different boundaries exhibit various styles of deformation, which we will list later in this lecture. And before talking about these plate boundaries in more details, I want to quickly discuss the case of the hotspot tracks, because hotspot tracks are essential in reconstructing motion of plates over geological time. So now we just travel to the Pacific and we go to Hawaii. You can recognize at the top here is the Aleutian Trench, and here's the Japan Kuri Trench, and there is a morphological feature here. This is the hotspot track and a list of chains and islands which are located in the Pacific. Along the Hawaii chain, so the volcanic activity dates to the present. And then there is a trend of ages to go older in time back into the past. So this hotspot track can be traced over the last 65 million years at least. What one can do with this, by dating the eruptions and measuring the distance, one can create this type of diagram, age distance diagram, and the slope here will be the velocity. You see that for this case it reaches 90 millimeters per year. It's basically 10 centimeters per year, which is close to 10 centimeters per year, which is close to actual GPS velocity of the Pacific plate. What could be the structure at depth that would explain this type of observation? The idea would be that somewhere in the asthenosphere there is a mantle plume that rises and creates anomalous magmatism and volcanism, and the plate here, the lithosphere, is moving past this hotspot with time. So the plate is moving past, and as times go, the location of volcanism is offsetted. Another emblematic hotspot is the Reunion hotspot in the Indian Ocean. So you can see the Reunion Island is here, and you have a series of trend of volcanic activity that can be traced back to the Deccan Traps about 65 million years ago. So let's discuss about plate boundaries, and we go down to the simplest vision, two-dimensional vision of a plate tectonic system. So at first order, we have oceanic ridges. This is where material is upwelling and where basically oceanic lithosphere is generated. So this is a divergent plate boundary. Away from this boundary, the plates are cooling, they are getting thicker, and they may start to sink. This would be a subduction zone. At this location, the plates are converging towards each other. So we have a divergent boundary here and a convergent boundary. Let's zoom a little bit on the mid-ocean ridge. So here you see a sketch of the ridge. You have the crust here. There is a bathymetry which is associated to the upwelling of the mantle. But as the mantle rises to the surface, it will undergo decompression, melting, because the pressure drops. So if you go on a depth temperature diagram here, there is a solidus for the mantle, and the rocks that are rising up towards the surface, they will at some point cross the solidus and start to melt. So here you would have partial melting, and this would produce liquids that want to erupt somehow. Therefore, part of the liquid reaches out the near surface or the surface directly, and it will form the basaltic crust with sequences of pillow lavas and sheeted dikes, and a big part of the melt remains trapped inside the lower oceanic crust, and they've actually formed the lower gabbroic crust. So the oceanic lithosphere, a standard thickness, can be of several kilometers. So how do we know the history of mid-ocean ridges? There are some features which are alternation of the polarity of the magnetic field. So we know from magnetostratigraphy that polarity reversals of the magnetic field can be precisely dated. They can be pinpointed through the geological history. One can also measure the magnetic field in the oceans and across the mid-ocean ridges. And this was an observation which was pivotal for the discovery of plate tectonics. Actually, the variation of the polarity of the magnetic field has been measured, and this could be then linked to knowledge from magnetostratigraphy. So what does it mean? In a way, one can measure the magnetic field along the oceanic floor and pinpoint the location of polarity reversals. If we know the age of the polarity reversal, and of course we know the distance which has been traveled to measure a profile, one can also compute the rate of oceanic plate divergence. So that's an example for the East Pacific rise. There's a correlation between time and position that gives a rate, here a velocity. So the age of the oceanic lithosphere now varies a lot, and you see that one of the most important features is that at mid-ocean ridge, the age is close to zero because the material is being generated there. So its age is basically of the present. So all the ridges are shown in red in this diagram because the material is being generated there. It's new. And if you go away from the ridges, you see that the color degrades to the yellow, then to the green, then to the blue. So if you get closer to the continents, you get older lithosphere. This is because there's a continuous production of material at the mid-ocean ridges. The oldest oceanic lithosphere are actually not so young, not so old with regard to the Earth history. It's about 180 to 280 million years. The thickness of the oceanic crust varies. There is a mean of 6 kilometers with the typical structure we discussed before, the gabbro and the basalt, but in some location of the Earth, extension at the mid-ocean ridges does not involve a lot of volcanisms, and in that case, the crustal thickness can be 0. So, now let's discuss subduction zones. That's a sketch view of the subduction system. You see here a descending lithosphere. This lithosphere has a velocity vector u, and it's moving with a consistent here velocity along the plate. The asthenosphere is right below. Above the subduction zone, you have the trench here, along which or above which sediments can be accreted. And you can have a volcanic line if there is a volcanism associated to the subduction zone. So how would this look in a cross-section view? So let's make a map view of this 2D section. If we go to a map view, a subduction zone will be represented by this symbol, which you may already know. On one side of the line, you have the lower plate, so this indicates the plate that will go down into the mantle, and on the other side, you have a line with triangles, and the triangles are pointing towards the upper plate. So that indicates the location of the plate which is above, basically here. Here is a fantastic example of oceanic subduction. That's the Tonga oceanic subduction. So you see a beautiful trench here. We are at the east of Australia, and that's a subduction zone between the Indo-Australian plate and the Pacific plate. Let's have a look at a map view. And a map view, the subduction symbol here is being used. So you see the little triangles are showing the upper plate all around the trench, both the Kermadec Trench and the Tonga Trench here. So the Australian plate is the upper plate and the Pacific plate is descending below. That's what we see. It's a very active zone also for volcanism. Remember, in 2022 there was this massive eruption from the Tonga Hapai. So there is a tremendous volcanic activity in this region. So how do we know that subduction zones actually exist? In fact, the subduction zones, they can be traced down in the deep upper mantle, at least, by using the location of hypocenters. So basically a plate that goes down also deforms and can be the source of seismicity. So seismologists can measure the depths and position of this earthquake. And when this is done in subduction zones, one can actually record a pattern that looks like a slab. So that's actually in the Tonga arc. You see distribution of earthquake hypocenters over here a distance of 1,000 kilometers horizontally and a depth extent of 700 kilometers. So yes, there is seismicity at depth, and the position of this seismicity potentially correlate with the position of a subducted tectonic plate. Another interesting data or measurements that can be done by a seismologist is the tomography. So basically, it is known that seismic waves, they will travel at different speeds if the mantle is hot or if the mantle is cold. In a subduction zone, a plate enters in the mantle is with a thermal structure which is colder than the ambient mantle. So it's bringing the cold from the surface down into the mantle. And basically, if one managed to reconstruct the seismic velocity at depth, one may image the position of the cold structure inside the plate. And that's again the example of the Tonga subduction zone. You have the Pacific plate on one side. The Tonga arc is here. The little circles are showing the position of hypocenters. You see a lot of hypocenters there and along this. And the color here is the anomaly of plate seismic velocity. So it's really a very nice correlation between the hypocenter and the variation of velocity. So seismic tomography can be used to trace back the position of slabs at depth. Another nice diagram here is showing you the reconstruction of different slabs. So if we use all this depth information, one can try to plot the shape and the morphology of slabs into the mantle. So you see here it's going down to 300 kilometers. What is nice to be seen is that subduction zones, they have different morphologies at depth. Some are very steep subduction zones and some can be very flat. So subduction has different shades. Now let's discuss the case of transform faults, and we go down to the South Indian Ocean now. You see this beautiful picture. What you see on this picture is a mid-ocean ridge which is dissected by transform faults. So what you can think about is that you have a ridge, and the ridge is a divergent boundary. So material goes, for example, to the right here and to the left there. If this ridge is broken by a fault, this part moves relative to this part, then you will end up with segments where the material from this ridge, from this side, is going towards the left, and the material from this ridge here is going towards the right. So at this boundary here, we have opposing sense of motion. So that is a fault here, a transform fault. On both sides of the ridge, you have plate velocities that go in the same direction, but they may go with different velocities, and that can trigger a fracture zone. So that's what we see, the trace of these fracture zones away from the transform faults. So let's make a map view of this structure. You see the symbol for an oceanic ridge is basically two lines here, two parallel lines. We have one ridge and another ridge. They are offsetted. They both have a divergent velocity, and at the location where the two ridges are connected, the sense of motion is opposite, so one plate moves with regard to the other. On the outer sides, we have fracture zones because there may be different velocities, so there can be deformation which is induced far away from the transform fault itself. This is also valid for the other side. There is the distance between this ridge and this ridge is called the ridge offset. So here are the symbols which are useful for the map view. We have the ridge, the transform will be the line, and the dotted line is the fracture zone. So let's zoom on this example from the South Indian Ocean. So if we go there, we will see the ridge, which is being offset. There is a segment of a ridge here, which is taken in the middle here. We have two transform faults with the solid lines here, and the fracture zones are on each side of this transform fault. One question here is, can we add more information about the kinematics of these systems? You should know senses of shear from structural geology. A sinistral sense of shear is when the block in front of you, if you're standing on this block, is moving towards the left. So think you're standing here and you look to this block and you see this block is moving towards the left. This is a sinistral sense of shear. For the dextral sense of shear, you think you're sitting on this plate here and you look in front of you and the plate in front of you is moving towards the right. That's a dextral sense of shear. So let's go back to our example. We have divergent motion here. We have a divergent motion there. This, if I'm sitting on this plate is moving towards the right. So this is a dextral sense of shear. If I look at this segment here, it's going to be a similar case. This plate is moving down and this plate is moving up. If I'm sitting on this plate here and I'm looking this plate is moving towards the right. So it's a dextral sense of shear. So let's now discuss the case of triple junctions. Here is a very emblematic triple junction. You will recognize the eastern edge of Africa. So that's the East African Rift, which is here. The Red Sea with the ridge here, and the Gulf of Aden, which is there. A triple junction is where three plate boundaries will meet. This one is called the alpha triple junctions, and that's the location where three divergent plate boundaries meet. So here we obviously have ridges that meet, and here we have a rift, not exactly a ridge, but that's a triple junction already. The ridge, triple junction. Another type of triple junction can be a trench, triple junction. So this means three subduction zones are going to meet and cross at one point. So now we travel to the Pacific. So we are close to Japan now. This is Mount Fuji. Tokyo is here. We have the Philippine Sea Plate. The Nankai Trough is here. The Sagami Trough is there. And if we move towards the east here, we have the Japan Trench. So at the Japan Trench, we have the Pacific Plate that subducts below the Eurasian Plate on that side and below the Philippine Sea Plate on that side. So we have three plates and three trenches interacting. Another famous triple junction is the Rivera triple junction. So we are going close to Mexico here, and California is at the north. What we have there is the interaction between the subduction zone, which is marked by a trench on this picture, transform faults, which are in this, which are dissecting a ridge here and a ridge segment there. So the interpretation of this, if we are at the south here, that's the Rivera triple junction, we have the subduction, ridge, transform, interaction. But if we look more carefully to the complex tectonic system that makes the border of the North American plate here, we see another very important feature here. There's basically the Sant Andreas fault, which is along this place here, and this one ends at the Mendocino triple junction. So what's the Mendocino triple junction? It's the interaction between transform fault, a subduction zone, the Cascadia subduction zone, and another transform. So that's a very nice example of a coastline which is here limited by two triple junction. How did this happen? That's a sketch taken from the book of Cox and Hart, and what you can imagine is that we're going to run forward in time. So we start from the past. We have a configuration where the boundary of the North American plate is marked by this segment here, and then we have the Pacific plate and the Farallon plate, and these are two oceanic plates. The Farallon plate is being subducted below the North America, and we have this divergent plate and transform faults. So we have this system here. This whole thing is going towards North America. It's being subducted at some point. The forward segment of the ridge and the transform fault are being subducted. So at this very moment, we basically generate the two triple junctions. So we have interaction, transform, transform, subduction here, and a subduction, ridge, transform, triple junction at the south. Now we move even forward in time, and you see that the triple junctions are migrating towards the north for this one. They are migrating along the subduction trench. So that's to conclude this lecture. In this lecture, I try to show you that the Earth is dynamic. So that's why we study geodynamics. We can reconstruct the Earth structure and the tectonic history, and that's the result of a lot of interactions between different disciplines of earth sciences, and to name a few would be seismology, geology, geomagnetism, geochronology, structural geology, stratigraphy, and that's just to name a few. We've discussed plate boundaries, including ridges where the oceanic lithosphere is produced, subduction zones where the lithospheric plates are being consumed, and we've discussed the case of oceanic transform faults where plates slide past each other. We've also discussed triple junctions, and this is where three plates boundary meet. So thanks a lot for your attention.